Hello everyone, so I hope you all are doing well. So in the previous session, I had covered the CFD analysis using ANSYS Fluent Part 1. In that, I had taken only the simple bus model to run the analysis. So here you could see the comparison with simple bus and with cam mirror bus with mirror bus, right? So this is a practical approach which everyone are trying to implement, that is the implementation of cam mirrors, and you could see the results drag force for simple it is 6169. When it comes to the cam mirror it is 6600. When it comes to the mirror it is 7400. You could even see the drag force variation. So according to this implementation we can consider the bus with cam mirror instead of the bus with mirrors. So we'll see how exactly we're gonna deal with these things. Yeah, so I'll take you through the steps which I had taken to just complete this project for all the three models, like the bus with simple model and with cam with mirror. Okay, so we'll see the same thing. So this is the setup which I had run. I'll take you through the basic modeling first. So the model is here. So I had imported the model. So once that is done, I had extruded the this particular enclosure, and then I had done with the boolean operation to just create the cavity inside accordingly, and then you're gonna have the final model. Okay, so if you want to see the section view of it, you can simply activate the section view from here, and you can take it, can draw a line like this for your reference, and you could see this is how the cavity is created. So next thing is to deal with the mesh that also showcase. The mesh, you can just refine it. I had used the normal coarse mesh, not exactly the finer one with respect to the manufacturing approach or the research and development approach which the people gonna use. Yep, so this is the model. Could see this is the bus with cam mirror, where we are not going to implement the practical mirror, so we're gonna remove it, and these locations we're gonna add the cameras. So inside the display we're gonna have the visuals to see these things to reduce the aerodynamic drag force on the this kind of vehicles. You can even implement on this bus, and even you can implement this thing in cars and even the heavy vehicles, even the transportation like the trucks and all. So everywhere we can able to implement this depending upon the requirement. Okay, yeah, so the thing is, I had created the name selection. First one is inlet, and then the backside outlet, and the wall, all the four, and then finally the burst model. To select this, you need to simply right click on it and select all. Once you do that, remove all the 4 plus 2 faces. Then all the faces will be selected by default. Okay, you don't need to worry about it. So the mesh, when it comes to mesh, I had used the mesh type. I'll just showcase the program controlled element order, and the size is curvature, not the uh, proximity and curvature. It will take you, like, it will refine more. And if you want to refine it again, you can use the mesh controls from here. Advanced refinement also you can try. And transition slow, the relevant center is fine, and the span angle direction is fine. So yeah, span angle center is fine. And the quality, I didn't change anything here. The smoothing, I had kept it high. And when it comes to inflation, I had taken the maximum layer as 10. Now more changes. Okay, remaining everything is as default. So once you do that, you can simply generate the mesh. So once you generate the mesh, you can go back to this and you can run the setup. So in the setup, what and all the things I had done, I'll showcase here. So the first thing is the model setup. The inlet outlet, automatically it will be taken. So the general tab, you're gonna have the options. So I'm going to run only this steady state, and I have done the same thing here. If you want to run the transient analysis for a certain period of time, you can even activate it. It might take a longer time, remember that. So the solver is a pressure based, not the density based. the gravity along y direction minus 9.81 meter per second square. When it's for velocity, I had taken it as kilometers per hour for my reference, because I'm okay with that, because I'm a bit confused with the conversion to kilometers to meter per second, so better directly activate the kilometers per hour. Then when it comes to the models, so there is no multi-phase we are going to consider, there is no energy transmission. And then when it comes to the viscous effect, I had taken the k epsilon, no more changes. So here in the k epsilon, I had used the model as realizable. Okay, by default you want to take the standard, so I had used the this method, the wall function, standard wall function I had used, so no more changes here. Okay, if you want to deal with the other things, you can even deal with the omega factors, and you can even deal with the standard methods and the RNG method and all. If you want to learn more about this, you can just use the ANSYS website, or you can even Google about these things, the parameters and all. Okay. Yep, so this is about the viscous effect, and remaining everything I haven't changed anything, by default is. And then when it comes to material, it is same for fluid is there, and for a solid is aluminum, by default it will take. The cell zone is by default, no need to change. Boundary condition when it comes to this, the inlet, which I had taken as the velocity, that is 100 kilometers per hour. The turbulence specification method is intensity and the viscosity ratio. You can even change it to k and epsilon method, and the values you had taken there, 1 and 1.2, can add it there, depends. Okay, for my consideration it is simple, so I didn't change anything, by default I took it. And then coming to the reference values, so I had computed this particular model from the inlet, and the area is this 21.83 frontal area. If you want to check this one, the direct method is you can directly go to this report, and you can use the projected areas from there. You can select the inlet and compute, you'll get the 21.83. okay, this is the frontal area which we are going to consider. Yep, so next thing is, by default if you keep it one, no issues, so software will take care of it. So if you are going to deal with this, that's better. Next thing, I'd gone through the methods. So here I changed the scheme to a simple only. When it comes to the turbulent kinetic energy and the turbulent dissipation rate, I've taken second order upward. Okay, no more changes here. When it comes to the report generations, I had added the CD and drag, that is description of drag, and the drag, if you want to add it new, you can simply right click and new, and force from here, lift and drag. So to add the drag, double click on it, and here you can specify option of drag and drag 2/3. So the wall is bus wall I had taken. So remember, while dealing with this, you need to activate the report generation and the report files and the create console. So for your reference, I can show how to create it. Go to this option. Let's say I want the coefficient of lift, you can select it, you can select the coefficient of lift, you can just rename it as CL, and file just defining it, report file and report plot and print console, so that you can get the result output here only to see that one thing, and later on once it is done you can compute it to see the results. Okay, I'm going to run it for the bus wall, so simply click on OK. Once the result is done, you can just open it and compute it to check the result. Okay, so once you're done with these things, you can initialize your model with the standard method, compute from the inlet and initialize it, and then just run this analysis for 200 iterations. Or else you can take more, but when it comes to the convergency, you can use the controls. Wait a minute. Yep. Oh, not here. Residuals. Let me just check. Residuals. Okay. So here, these are the convergence criteria. Okay, it is absolute, and when it comes to the absolute criteria, it is 0.001. So while I was in graduation, I used to run this analysis up to more than 900,000 iterations to get the result converged, but here I didn't done it, only 200 iterations, and I had taken the approximate values. So if you want to get the more absolute results, you can just set it to 1 into 10 raised to minus 6, or then 1 into 10 raised to minus 5, depending upon your requirement. You can set the criteria, absolute criteria, and run the analysis. Okay, so for me, I had simply run the analysis up to 200 iterations to just get it off it. So now if you want to, like, once the result is done, you can simply click on compute to get the CD value. Here it is 0.63994. And if you want to check the drag, double click on it and use the okay, I'll get the value. Drag force is 6,602.2938, right? So like this you can able to deal with these things. So when it comes to the results, I'll showcase these things, how to just create the results and how to create the counters and other plots. Okay, we'll see that things. Yeah, when it comes to the results, you can use this drop down location. You can create the plane. Okay, if you just run the results there, you can set it along xy plane and you can define the direction along z, how much you want. So for my convenience, I'll activate the bus wall to see the preview of the wall, like the plane which I'm going to create. I'll take the value, so it is 1 meter, apply, and you could see the placement. If you want to change the placement, you can just simply add the values there and you can set it like this. So like this you can create the multiple planes. So after that you can just create the uh, plot, and here I'm going to use the vector plot. So for this I'll use the velocity on plane 2, and you could see on plane 2 is exactly on the camera, and this is how the flow is happening on that region. You can preview the model and you could see how it is there. Okay, you can even have this for the result presentation. You can capture this images, and after that you can deal with the other plots. So let's say I want again one more vector plot exactly at the plane 2, plane 1, okay, which I had created at the center. This is how it's gonna vary there. So depending on the locations and the mesh, you'll get the more finer result output. Remember that. So now I'll just create the contour plot, that is pressure plot on the surface plot, that is. In SolidWorks flow simulation we call it like that, the pressure plot, and it is on all the bus wall. The contours I'll change it to 1, and once you apply it I'll get this. Okay, this is the contour plot, that is pressure plot on the entire bus wall, the surfaces of the bus which I had considered. So you can remove these vector plots and just to preview this model. Okay, yep, this is about the bus width camera, and these are the result plots, like the contour plot, vector plots, and if you want you can even add the other plots. So right now I'm not going to deal with these things. So when it comes to next one, the bus width mirror. So I had done the same thing, created the plane and created these all the vector plots and the surface plots, the pressure plots. You could see how it is varying, right? And this is the pressure plot finally, and this is how it's gonna look like. And to compare the results finally, to just showcase how the results is varying from the model with simple bus model with cam and with mirror, we'll see these things. So this is the model with mirror. You can go to this report definitions, double click on it and just compute it to check the result. It is 0.78, and here it is 0.7400 something. Okay, and when it comes to the model with camera, you can simply go to the report definitions, and here you can just check the same thing, just double click on it and compute. And this is the CD value coefficient of drag, and this is the drag force 6,600, which is comparatively less than the value. Okay, so this is how we can able to just compare the results. Yep, so that's all about this session, guys. I hope you got to know about the ANSYS Fluent, how to use it, and how to deal with the CFD analysis using the simple basic models and simple mesh. And about this project, regarding this project, I had taken the three models into account, that is simple bus and the bus with cam mirror and bus with the normal mirror, and I had ran the analysis for all the three models with the same boundary conditions, and I had compared the results, and we had seen the drag force and the CD values, which are comparatively good for the cam mirror bus when it compared to the bus with the normal mirror. So that's what the outcome of this particular the project which I had created. That's all about, guys. Thank you. Stay tuned. Bye everyone.